Hi everyone, this is video number 8 of our T3 complex number lecture. Currently on the screen is page 24 of our T3 tutorial 10 notes. On pages 24 and 25, we will learn about roots of a complex number. This is actually not something which is totally new because earlier on page 8 of this chapter, we have learned about square roots of a complex number. Here, we are just expanding our study to include nth root in general, which means we will learn how to find cube root, fourth root, fifth root, and so on for a complex number. Okay, first let's revisit the concept of argument z. Okay, so by definition, argument z is the angle measured from the positive x direction. Okay, so in diagram A, we can see that if we start measuring the angle from the positive x direction in the green colored along the green colored dotted line, and we start to measure an angle towards the vector representation of the complex number z, and then that would be the theta would be the argument of the complex number z. And in this diagram, we are illustrating z to be a number whose point representation is in the first quadrant. And we call the point representation as point P in figure 8. Point number 1 Roman 2 says, however, as figure B shows, you can increase theta by 2 pi and still obtain the same line in the xy plane. And so that means there are more than one way to obtain the same direction. The slanted arrow is a vector representation of the complex number z, and if we rotate by one more cycle, we can still end up with the same direction. So that means we can also write argument of z as theta plus 2 pi. So it is correct to say argument of z is theta. It is also correct to say argument of z is theta plus 2 pi. But of course, theta plus 2 pi will not be in the principal range. This is not a principal argument. But it is a correct argument. But is a correct argument. Theta plus 2 pi is just not in principal range, but it doesn't mean it's wrong. Right. Then point number 3 says, in general, as indicated in figure C, any integer multiple of 2 pi can be added to or subtracted from argument of z without affecting the Cartesian form of the complex number, because you will still end up having the same direction. Right. So diagram C shows us that if we keep rotating, and so if we start from the direction of theta, and we keep rotating by an integer number of cycles, you will still always end up at the same direction. And point number 3, the sentence there also say, not only we can add by any integer multiple of 2 pi, we can also subtract. Right? So we can also say argument of z is theta minus 2 pi. It is also a correct argument. Although it's not going to be in principal range, it is still a correct argument nonetheless. Okay. So for example, if you look at my figure A, if I start from the direction indicated by theta, I can go backwards by one cycle. Then I will have theta minus 2 pi. And I will still end up with the same direction. So in general, if argument z equals to theta is a correct argument, then argument of z can be written as theta plus 2k pi to include all the correct arguments, all the possible correct arguments. And here, k must be an integer. Okay, just one quick example. Argument of 1 plus I. The traditional method, we know it is point with coordinates 1, 1 in quadrant 1. So you will have inverse tangent of 1 over 1, which will give you pi over 4. Okay, so if we know argument of 1 plus I is pi over 4, then it must be correct to say argument of 1 plus I is pi over 4 plus 2k pi, where k can be any integer. So when I say k can be any integer, I include all positive integers, negative integers, and 0. Right, so this would include all the correct arguments. For 1 plus I. Okay, so when you have pi over 4 plus 2k pi, this expression, it has included all correct arguments for 1 plus I. And of course, there are infinitely many correct arguments since there are infinitely many integers k. Okay. Right, then let's move to point number 2. Of unity. Okay, unity is just a more fancy name for the number 1. Okay. Nothing special about the word unity. Unity is just a fancy name for the number 1. So nothing special about unity. So when they say roots of unity is referring to roots of the number 1. Okay. So an n root of unity, or the n root of the number 1, where n is a positive integer, is a number z satisfying the equation z power n equals 1. Okay, so since they're asking for the n root of 1, then we are effectively solving for z in the equation z power n equals 1. So you just solve for z in this equation. Then your values of z will be the n root of 1. Okay. Example 9. Find the cube roots of unity, that is, solve the equation z cubed equals 1. Then give your answers in Cartesian form. When solving for square roots on page 8 of this chapter, recall the procedure back then on page 8. So on page 8 of this chapter, for example, if we are asked to find square roots of the complex number, let's say 2 plus 3i, then we are going to let z squared equals 2 plus 3i, and we'll let z equals x plus yi, where x and y are real numbers. And then you will have x plus yi squared equals 2 plus 3i, and you will proceed to solve further by comparing real parts and comparing imaginary parts. Okay, so when solving square roots, it is feasible to do it in Cartesian form. But when solving for cube roots or anything of a higher degree, or anything of a higher order, right, then you would encounter very tedious expressions if you do it using the Cartesian form. Okay, so for example, when finding cube roots, find cube roots of 2 plus 3i. Okay, so if you still use the same method, you let z cubed equals 2 plus 3i. Then you let z equals x plus yi, where x and y are real. And then you will encounter problems later. X plus yi cubed equals to 2 plus 3i. Later, when you try to compare real parts and imaginary parts, the expression that you get will be pretty hard to solve. So to avoid this kind of tedious algebra, whenever we need to solve for roots of a higher order, cube roots and above, we are going to use the polar form instead. We'll prefer to use a polar form instead. And in example 9, it shows you the procedure. So example 9, find the cube roots of 1. So they say solve the equation z cube equals to 1, give your answers in Cartesian form. And so the solution is already partially printed for you. And so the first step is to express the right-hand side in a polar form. Either modulus argument form or exponential form. It's easier to do it in polar form rather than the Cartesian form. And whenever your the root that you are trying to solve for is having order 3 or higher. Right, so step 1, convert the number 1 into polar form. Convert 1 into polar form. Convert this 1, which is the right hand side of the equation, into polar form. And so polar form can be either modulus argument form or the exponential form, whichever that you prefer. Right, so obviously modulus of the number 1 must be 1, because if you visualize the Argand diagram, you have 1 being a real number on the real axis. So its vector representation obviously has a length of 1. And the argument of the number 1 must be 0. Because there is a 0 angle made between the positive real direction and the black colored vector in the diagram. And that also means we can write 1 as r bracket cos theta plus I sine theta. And so here I'm using modulus argument form. And recall that modulus argument form means you write z as, to avoid confusion, I better not use the symbol z here. I mean, you write the complex number as r bracket cos theta plus I sine theta. Okay. So after having this, let's go back to the notes and see what is step 2. Step 2 says you will add 2k pi to the argument data on the right hand side. Okay. So we are trying to solve the equation z cube equals to 1. We want to solve z cube equals to 1. And since in step 1 we have already converted 1 into polar form, of course we can now write the 1 as 1 cos 0 plus I sine 0. Okay, so under step 2, in step 2 it says we will add, okay, this 1 is redundant. I will just choose to not write the 1 at all. Okay. So it says you will add 2k pi to the angle in the cos and sine terms. So this 0 here, you will write it as 0 plus 2k pi. And same happens here, 0 plus 2k pi. Okay, and then we'll state where k can be any integer. Okay. Okay, next step, I will just make the angle look nicer. The 0 is redundant there. I'll just write it in a simpler form of 2k pi plus I sine 2k pi. Now, when the power 3 is moved over to the other side, it becomes power 1/3. Or in other words, we just apply power 1/3 to both sides. So that the left hand side is converted to just a single z. So left hand side just becomes a single z, and the right hand side has a power 1/3 applied to it. So you have cos of 2k pi plus I sine of 2k pi. Yeah, for clarity, I will just write the outer layer bracket using square brackets. Okay. Okay, now we can apply the Moivre's theorem. We can apply the Moivre's theorem because we have the form cos theta plus I sine theta. Inside the square bracket, we have the form cos theta plus I sine theta. Okay, so we can apply the Moivre's theorem, which says the 1/3 can just be multiplied to the angle directly. Okay, so Z becomes cos of 2k pi over 3 plus I sine 2k pi over 3. Okay, let's look back at the notes and see what the note says. The note says now, step 3, they tell us to solve for Z, which we have already solved for Z by moving the power 3 over to become power 1/3. And upon applying the Moivre's theorem, we obtain the most current line so far. We have cos 2k pi over 3 plus I sine 2k pi over 3. Okay, then step 3 in the note says, it's time to choose 3 consecutive integers for k. Now, when solving for square roots of a complex number, we know there will be 2 solutions. Following the same pattern, when solving for cube roots, we expect to have 3 solutions. When you solve for fourth roots, you expect to have 4 solutions, and so on. Right? So they say choose 3 consecutive integers for k to generate the 3 different solutions. Okay. And here they also say usually we choose 3 integers about 0. About 0 means the 3 integers which are nearest to 0 to ensure that the argument is in the principal range. Okay. Now this is how we choose the integers. Okay, so in your mind, you can visualize a number line. You can visualize a number line. And you list down the integers which are near to 0. So what are the 3 integers which are nearest to 0, including 0 itself? Of course, 0 must be the nearest one to 0. The second and third nearest must be 1 and minus 1. So now we say where k is -1, 0, or 1. Where k is -1, 0, or 1. Then what is step 4? Well, step 4 says just sub in the chosen values of k to generate the 3 different solutions. Okay. Now, why must we select integers which are near to 0? Okay. Now, if you follow this guideline of selecting integers which are near to 0, uh, most of the time, after you sub in the -1, 0, and 1, if those are the 3 integers nearest to 0, they will give you your final solution where your argument is in the principal range. Okay, so if you follow the guideline of selecting integers which are near to 0, you will conveniently get argument values which are in the principal range. So now I will just sub in -1, 0, and 1. And so when I sub in k equals -1, I will have cos of -2 pi over 3, -2 pi over 3 plus I sine of -2 pi over 3. When I sub in k equals 0, I will have cos of 0 plus I sine 0. When I sub in 1, I will have cos of 2 pi over 3 plus I sine 2 pi over 3. Now you notice that the arguments that you have in your 3 solutions, minus 2 pi over 3, 0, and 2 pi over 3, they are all within the principal range. And recall that the principal argument or the principal range of argument is such that your angle theta is between minus pi to pi. Right? So if you check these three arguments, minus 2 pi over 3, 0, and 2 pi over 3, they are all within the principal range. Right? So this is the benefit of selecting three consecutive integers which are nearest to 0 as the value of k. Right. This question wants our answer in Cartesian form, and they actually didn't prohibit us from using the calculator. So you can actually use a calculator to press out what is cos of minus 2 pi over 3 and so on. But anyway, I will just do it the manual way, just to show you how that can be done. Okay, so for cos, you can swallow away the negative sign. So you have cos of 2 pi over 3. This is minus I sine 2 pi over 3. And because sine can pull out the negative from the angle. And cos 0 is just 1, sine 0 is just 0. But this cos of 2 pi over 3, in the ASTC diagram, you are left with basic angle of pi over 3. And 2 pi over 3 is a quadrant 2 angle. And so cos of 2 pi over 3 can be replaced by minus cos pi over 3. This is plus I sine pi over 3. And because sine is positive in the second quadrant. And now cos of 2 pi over 3 again are replaced by minus cos pi over 3. And sine of 2 pi over 3 is now negative sine pi over 3. Sorry, there shouldn't be a negative here. It's just sine pi over 3. And because sine is positive in the second quadrant. The second solution is simply 1. The third solution is minus 1/2 plus Z3 over 2i. And so I just write my first solution nicely now, negative 1/2 and minus Z3 over 2i. This is 1, this is minus 1/2 plus Z3 over 2i. Yeah, and these are your three solutions. Okay, so since this question asks for cube roots of unity, so at the end, you will just say cube roots of unity. They are negative 1/2 minus Z3 over 2, 1, and minus 1/2 plus Z3 over 2i. And that's it. Yeah, so this is the procedure to follow when solving cube roots, fourth roots, or roots of any higher order. Okay. Then if you're wondering, can you also solve for square roots using this method? Yes, you can. Right, so in some of the exam questions, if the complex number is already given or already available in polar form, and you are asked to find the square roots of that complex number, then it will be more convenient for you to just solve it using this method on the screen right now. Right, so if you need to solve for square roots of a complex number which is already in polar form, then you can use the current method on the screen now to solve. So it's not a must to convert to Cartesian form to solve for square roots. Square roots can also be solved for when you have polar form. Just follow this procedure here. Okay, now I have a few additional comments here. Okay. Now, just now, when it comes to the step of deciding on the integer values of k, if you solve for cube roots, then you should take 3 consecutive integers which are nearest to 0. Why we take 3 but not any other number is because for cube roots, we expect to have 3 different solutions. And then some people may ask, what if we solve for fourth root? When we solve for fourth root, what are the 4 integers which are nearest to 0? So when solving for fourth roots, how to choose 4 integer values for k? Okay, so if we visualize the number line, obviously 0 must be chosen because 0 is the nearest to 0. Okay, the second and third nearest must be 1 and -1. Hey, but our fourth choice, we have a dilemma here. We are not sure whether we should take -2 or +2. We are not sure. And so how do we decide? Well, we will decide based on which of these 2 integer values, -2 or 2, will among these 2, we will pick the one that gives an argument in the principal range. Yeah, so this is how we decide. Later, there will be one exercise question that asks us to solve for the fourth root. And so later you will see how it works. Okay. And similarly, if you use the polar method to solve for square roots, when solving for square roots, how to choose your k, you will need to choose 2 values of k. Obviously, 0 must be chosen, but what is the second nearest to 0? Again, we have a dilemma. We are not sure. So the guideline to decide is the same. We'll pick the one among -1 and 1. It will pick the integer value that gives an argument in the principal range when substituted into our answer. Right. Okay, so this is how we choose the consecutive integer values for k. Okay. So 2 things you have to know. First is if you are solving for square roots, you choose 2 consecutive integers. For cube roots, you choose 3 integers. For fourth root, you choose 4 integers, and so on. And we have to choose consecutive integers which are nearest to 0 to ensure that the solution that we get will have arguments in the principal range. Okay. And when there is an even number of integers that you should choose, you will have a dilemma situation where you are not sure which one to pick as your last integer to be included. For example, when solving for fourth roots, there's no doubt that -1, 0, and 1 must be picked. But between -2 and 2, we have a dilemma. And the way to decide is we will pick the one that gives an argument in the principal range. It's the same for square roots. When you have a dilemma between -1 and 1, you follow the same guideline to decide. Okay. Now, looking back at the cube roots of unity, some people may wonder, isn't it that usually when we solve x cubed equals 1, we usually just say x equals to cube root of 1 and we just have one solution. But why now we end up having 3 solutions? What is the equation that we solve at the beginning? We solve z cubed equals to 1. So isn't this the same equation as x cubed equals to 1? Isn't this the same equation? But why instead of getting only one solution, now we get 3 solutions? The reason is because usually, I mean, before we learn complex number, all the questions that we encounter were dealing with only real numbers. So x cubed equals to 1, x equals to 1, this is the only real solution. I mean real number solution. It is the only real number solution. But when you allow complex solutions, there are actually 3 solutions. Okay. Oh wait, I think just now I forgot to write down an I here, sorry. Yeah. Okay, I missed out the I just now. Yeah, so yeah, there are actually 2 complex solutions here. These are the complex solutions. And this is the only real solution. Okay, so what we have done over the years, x cubed equals to 1 means x equals to 1 is the only solution. What we have done over the years was correct when we only care about real solutions. Okay, because there is indeed only one real solution for the equation x cubed equals to 1. Okay, but when you allow complex solutions to be included, then there are actually 3 solutions. Now, if we plot out the point representations of these 3 complex solutions on an Argand diagram, what will we get? Okay. Easier to plot if it'll be easier to understand why the shape looks that way if we look at the modulus argument form of these 3 solutions. We'll just paste the solutions over here in modulus argument form. And I would also paste over the Cartesian form, the solutions in Cartesian form, so that later you can compare. Yeah. Okay, so this is in modulus argument form. These are solutions in Cartesian form. Okay. Now, from the modulus argument form, we know that the R in each of these 3 solutions are all 1. Okay, there's an invisible 1 here. There's an invisible 1, and similarly, there's an invisible 1 here. Okay, so that means if I plot out the point representation of these 3 solutions on an Argand diagram, they will be located along the circumference of a unit circle centered at the origin. Okay, so I repeat, the point representations of these 3 cube roots of unity, okay, they will be located along the circumference of a unit circle centered at the origin. Okay, because the R is 1. The R is 1 for all 3 of my solution. What is the meaning of R equals to 1? It means the distance from origin to the point representation is exactly 1 unit. And we know if we draw a unit circle centered at the origin, any point along the circumference, it will be at a distance of 1 unit away from the origin. So let me just draw a circle here. So any point along the circumference of this circle, it will have a distance of 1 unit away from the origin. So what about the arguments? The first solution has argument of minus 2 pi over 3. Minus 2 pi over 3 is negative 120 degrees. So that means I have to measure 120 degrees like this. So here I'm labeling the magnitude of the angle. So it is roughly here. Then okay, so this point, let's call it Z1. Okay, so Z1 is having a distance of 1 unit away from the origin, and it is at an angle of minus 2 pi over 3. It measured from the positive real direction. Okay. Then what about my second solution? My second solution has modulus of 1 and argument of 0. So it will be this point here, which I label as Z2. Right, that's my second solution. Okay, so the point Z2 is at a distance of 1 unit away from the origin, and is making an angle of 0 with the positive real axis. Then my third solution is again 1 unit away from origin and makes an angle of 2 pi over 3 measured from the positive real direction. So it will be here. Again, 2 pi over 3. This is my Z3, 1 unit away from the origin. And what is the remaining angle in purple color here? If we really calculate, one full cycle is 2 pi. 2 pi minus 2 pi over 3 minus another 2 pi over 3. That leaves us with just 2 pi over 3. So we see that these three angles are equal. So that means the 360 degrees is equally divided. Like you kind of have a circle equally divided into three sectors, divided into three equal sectors by the three blue lines. Okay. And this is not a coincidence. In fact, this is such kind of observation is sure to happen whenever we find roots of unity, whether it's cube root, fourth root, fifth roots of unity. The location of the roots on the Argand diagram, it will always be along the unit circle, and the arguments of each of the roots, it will be such that when you draw a diagram like this, the unit circle will be divided into sectors of equal sizes. Okay. Now, just to convince you that what I said is true, let's consider the thing that we are familiar with. Z squared equals 1. We know there are two solutions. Z equals to plus minus square root 1, which is plus minus 1. These are in fact the only two solutions. And there are no complex roots for Z squared equals to 1. Okay. Now, what are plus 1 and minus 1? Okay. On the Argand diagram, 1 or minus 1. So I have these two numbers to be plotted out. Okay. So if this is 0, this is 1, this is negative 1. 1 and minus 1 are real numbers. So they must be points on the real axis. And so this is my first solution, Z1. This is my second solution, Z2. And so it is still true that the square roots of unity, these two are the square roots of unity. It is still true that square roots of unity lie on the circumference of the unit circle centered at the origin. Because they are both 1 unit away from origin. And when I draw a line from the origin towards the point representation of these two roots, I do have the circle divided into two equal sectors, where the angle made in the middle, the angle made at the origin is pi here and another pi here. So the full cycle of 2 pi is equally divided into two parts. Okay. And with that, you can also foresee that if I ask for the fourth roots of unity, if I ask for z power 4 equals to 1, then what are the solutions for z? You can actually guess what the solutions are by looking at your Argand diagram. Now that you know all the solutions for roots of unity, it must be along the circumference of the unit circle. And without doing any computation, you can already tell that z equals to 1. It must be one of the four roots. Because 1 power 4 is 1. So z equals to 1, it must be one of the four roots. We know there are three other roots, but at least we know 1 must be one of the four roots. And where is the point representation of 1? It will be here. It will be here, right on the real axis. Now, since we know for roots of unity, they will be evenly distributed along the circumference of the unit circle. And since one full cycle is 2 pi, that means um, this circle will be divided into 4 equal sectors, making 90 degrees at the center. Making 90 degrees at the center. And so you can expect your second solution to be up here. So if I call this Z1, this will be Z2, this will be Z3, and this will be Z4. Okay, so if I list down the solutions, Z2 will be the solution I, Z3 is the solution -1, Z4 will be the solution -I. And so if you really check, I power 4, we know it is 1. Okay? That means I is a valid solution. -1 power 4 is also 1. So -1 is a valid solution. And negative I power 4, it is, sorry, negative I with a power 4 on the outside. Negative I power 4 is just I power 4. And because when we have an even power, the negative disappears, and I power 4 is the same as 1. And so again, this is negative I is another valid solution. And so yeah, Z1, Z2, Z3, and Z4 on the diagram, they are indeed the four fourth roots of unity. And so just some interesting observation here regarding roots of unity. Their point representations will be equally distributed, evenly distributed along the circumference of a unit circle centered at the origin. Okay. Right, now let's read point number 3 on page 25. N root of a complex number in general. So here it says to solve the equation z power n equals to w, where w can be any complex number and w is not 0, we can follow the same steps as in example 9 above. Right, so it's saying that if you need to solve, let's say, z cubed equals to 1 plus 4i, then you will just follow the same procedure as in example 9 that we just done, where you first convert this into polar form. Convert to polar form. And then next, you add the argument in the polar form by 2k pi, where k can take any integer. Then next, you would move your power 3 over. Okay, so let me just summarize the step again. Step 1, convert the right hand side to polar form. Step 2, add 2k pi to the argument of the polar form. Step 3, let's solve for z by taking powers. Take power 1/3 on both sides. And here to avoid confusion, I don't prefer people to use cube roots. I mean the cube root symbol here. Like when we take power 1/3, just now in example 9, yeah, I would prefer people to write power 1/3 rather than writing cube root of cos 2k pi plus I sine 2k pi. The cube root symbol covering a complex number is not preferred because that might lead to confusion. Furthermore, when you write it as something power 1/3, it is more intuitive to apply the de Moivre's theorem. Okay. Right. Yeah. So step 3, solve for z by taking power 1/3 on both sides. Then decide which values of k to use, which three values of k to use. It will take three consecutive integers nearest to 0. Step 4, list down the three solutions. So sub in the k, sub in the three chosen k values, and list down the solutions. Right, now let's move to exercise 7 and do some practice. Okay, find the two square roots of 9ei pi over 3, giving your answers in the form rei theta. Okay, so they want exponential form, where r is more than 0 and theta is between minus pi to pi. This is just the usual default requirement. R is positive and theta is in the principal range. Now, because the complex number given is in exponential form, your answer is needed to be in exponential form. So it will be easy or convenient to just do everything in exponential form. We are not going to convert to Cartesian form. Earlier in page 8 of this chapter, we have learned how to do square roots in Cartesian form, but here we will do this question entirely in exponential form. We will not go through the trouble of converting exponential to Cartesian, then Cartesian back to exponential. That will be unnecessarily tedious. Now, so to find the two square roots of 9ei pi over 3, I will let z squared to be equal to 9ei pi over 3, and the aim is to solve for z. I want to solve for z here. And so solving for z will be the same as taking square roots. Okay. So, okay, please don't write z equals to plus minus square root 9ei pi over 3. It doesn't work this way when you have a complex number. It doesn't work this way. So you have to follow the procedure just now. Now that we have things in exponential form, it's still the same procedure, but your working will just look a bit different. Just now in example 9, we were using modest argument form. Here we use exponential form, but the idea is the same. So first, the step 1 is not needed. Step 1 was originally to convert the complex number from Cartesian to polar form, but this number is already in polar form. This is already polar. Already polar form, so there's no need to do conversion. It will proceed to step 2, or maybe before step 2, I will just write it in this form so that it's more obvious that the argument is pi over 3. Okay, next is to add 2k pi to the argument, or the theta part. The theta is pi over 3, so you just add by 2k pi. Pi over 3 plus 2k pi for whatever integer k, it will still point to the same direction. So this is still correct. The equation is still correct. Where k is an integer. Okay, next, the power 2 move over to the other side. It becomes a power 1/2. It becomes a power 1/2. Then now we distribute the 1/2 to the 9 and also to the exponential term. So I have 9 power 1/2, which will later become 3. And when my 1/2 gets multiplied, I will have EI pi over 6 plus K pi. Nine power half becomes 3. This is EI. Just do some algebra here. Make it to have a common denominator of 6, and I have 1 plus 6K times pi. Now it's time to decide what are the two consecutive integer value of k that we should take here. Obviously, 0 must be taken because on the number line, 0 is the nearest to 0. But between 1 and -1, which one should we choose? It depends on which value of k, when substituted inside here, will give us an answer in the principal range. Okay. So you can easily just mentally check. Okay, when I sub k equals to 1, I will get 7 pi over 6, which is beyond pi. It's beyond pi, therefore it's not in principal range. Okay, so if 1 shouldn't be taken, -1 must be the one. Okay, so I will take -1. Okay, and if you really check whether you will get an answer in the principal range when k is -1, you can of course do some mental checking. When k is -1, I have 1 minus 6 times pi at the numerator. So that's -5 pi over 6. And this is indeed somewhere between -pi to pi. So this will be a correct principal argument. Then the last step is just to list down the two solutions, substituting in your k. So there's 3ei, this is 1 plus 0 pi over 6, 3ei 1 minus 6 pi over 6. So final answer, 3ei times pi over 6 and 3ei times -5 pi over 6. Yep, so these are your two answers. And that's it. If you prefer, some people like to multiply I to the numerator at the power. Some people prefer to write things like I pi over 6, 3e negative 5i pi over 6. And this is just another equivalent form. This last step is optional. Right. So that's all for this question 1. Okay, the two square roots of 9ei pi over 3. Now we'll move to the next question 2. This question 2 asks for answer in modulus argument form. And they have the default requirement, R must be positive, theta must be the principal range. So there's a note at the bottom here which says the form cert2 cos pi over 3 minus I sin pi over 3 is not modulus argument form because you have a minus in the middle here. Okay, and thus is not accepted as the answer. Okay, because the answer specifically say they want modulus argument form. Right, so when you have a minus in between, it is not modulus argument form and hence cannot be accepted as a final answer. Right, so just be aware of that. Right. Now, since they want our answer in modulus argument form, it, no, they have this thing power 1/2, which is the same as square root. Okay, power 1/2 means to find the square root. Okay, so this question is actually asking for find square root of -1 minus I the 3. Yeah, it's actually asking for this. Okay, so to find square root of this, we will let z squared equals -1 minus I the 3. Since they want our answer in modulus argument form, it will be convenient to first convert uh, the -1 minus I the 3 into modulus argument form first. And then we'll do everything in modulus argument form so that at the end, there's no need to do any conversion. It will do conversion at the beginning. So modulus of -1 minus I the 3, that is cert of -1 squared plus minus the 3 squared. I'm using the formula square root of x squared plus y squared. And this gives me a cert of 4, which is 2. Argument of -1 minus I the 3. If you visualize the argon diagram, this will be a point in quadrant 3, -1, -3, where we'll have to take minus pi and plus back by the basic angle. So I have minus pi plus inverse tangent of modulus y over x, where your y is -3, x is -1. Minus pi plus inverse tangent of sec3, this is minus pi plus pi over 3, that gives -2 pi over 3. Therefore, -1 minus I sec3 can be now written as r is 2, followed by cos theta plus I sin theta. So this is a modulus argument form, and I'll keep it this way. Okay, so earlier we had this equation, z squared equals -1 minus I sec3. This now becomes z squared equals 2 bracket, I just use the square bracket here for clarity. Then now next I will move the power 2 over to the other side so that my 2 gets the power of 1/2, and this cos of -2 pi over 3 plus I sine of -2 pi over 3 also gets the power of 1/2. The power of 1/2 appears here and here. The 2 to the power of 1/2 is simply square root 2. It's just a real number, nothing special about it. Okay. This 1/2 by De Moivre's theorem, I can just multiply it inside. I can safely apply De Moivre's theorem because I have the modulus argument form inside the square bracket. I have the cos theta plus I sin theta form. Recall from De Moivre's theorem, which says cos theta plus I sin theta to the n is the same as cos n theta plus I sin n theta. Okay, so here we have cos of minus pi over 3. Oh, wait. I missed out one step, sorry. I shouldn't apply the Moivre's theorem too quickly. Yeah, in fact, the power 1/2 also, I shouldn't move it there too quickly. Yeah, I missed out one step. I should have added by 2k pi first. I should have added by 2k pi first. Or else, I won't get two solutions later. Yeah, so during the exam, if you happen to forget to get 2k pi, somewhere in the middle of your working, you will realize that there is something wrong. Because if you forget the 2k pi, uh, you won't get two solutions at the end. So you will realize if you forget that. Okay. So minus 2 pi over 3 plus 2k pi plus I sine minus 2 pi over 3 plus 2k pi. And here I say where k takes any integer value. And then now only I move my power 2 to the other side. So that's 2 to the half. And yeah, this thing also to the power half. And the power half appears at these two places. 2 power half at the front is just a square root of 2. That's just a real number, nothing special. Now this power half can be multiplied into the angle by the Moivre's theorem because we have the form cos theta plus I sin theta to the power n. And so when this gets multiplied, you will have minus pi over 3 plus 2, no, it's not 2 anymore, it's k pi only, plus I sine minus pi over 3 plus k pi. And close. This is by the Moivre's theorem. And now it's time to decide which two values to choose for k. Obviously, 0 is one of the integers that we must choose because it's the nearest to 0. Then between 1 and -1, which one to choose? If you sub a 1 here, you will get minus pi over 3 plus pi, which gives you 2 pi over 3 that is in the principal range. So 1 is the choice. 1 is a choice. If you sub in -1, you will get a minus 4 pi over 3. If you sub in a -1, you will get a minus 4 pi over 3, which is smaller than minus pi, and therefore we don't want it. Okay. Yeah, so now it's time to sub in your k to get your two solutions. You have sub 2. When I sub 0, I have cos of minus pi over 3 plus I sine of minus pi over 3. When I sub in k equals to 1, I have sub 2 cos of 2 pi over 3 plus I sine 2 pi over 3. Yeah. And so it's important to let your reader know what values of k that you are substituting in your working. And so it's important to state the values of k that you're about to sub in. Okay. Okay, so there are some negative angles here, but that's not to worry about them because our solution here, which I underline in yellow, is already in the modulus argument form. And so we'll just leave it in that form. We are not going to do any modification to it. It is okay to have negative angles because this negative pi over 3 is within the principal range. Right. Yeah, so these are your two solutions. And at the end, just conclude. Um, they are asking for values of -1 minus I to 3 to the power half. So at the end, just conclude. Values of -1 minus I to 3 to the power half. They are set to cos minus pi over 3 plus I sine minus pi over 3. Okay, or set to cos 2 pi over 3 plus I sine 2 pi over 3. And this is your final answer. Okay. When writing modulus argument form, okay, don't forget this layer of bracket that I'm coloring in pink. Don't forget this layer of bracket, because without the brackets, the meaning would become different. Okay, so this pink colored pair of brackets are important, okay, when writing your modulus argument form. If we don't put this pink colored brackets there, then your cert2, it won't get distributed to the I sine term. Okay, so that pink colored bracket is important. Right. Before I forget, I would like to go back to just now the cube roots of unity. Cube roots of unity, yeah, here's the diagram. Okay, so just now I forgot to talk about the Cartesian form of the three solutions here. And this is the cube roots of unity. Okay, so if you really check the three solutions, okay, the Z1, which has -half minus Z3 over 2i, it actually makes sense for it to be here. -half is roughly here, and this number will be minus Z3 over 2, which is quite near to -1. So it makes sense. Okay, well, your Z3, your third solution, has an x coordinate of -half, so it makes sense as well for it to be here. And plus Z3 over 2 is quite near to 1. And of course, your second solution, the real number 1 is on the real axis when the real number is equal to 1. So it's right here. Z2 is there, and the position makes sense. Okay. Okay, now let me go back to question 3 of page 25, with the last question on page 25. Okay, this is a more challenging question because it involves fourth roots. Okay, they want your answer in exponential form, okay, where r is more than 0, theta and the principal range. These are just default requirements. It show the roots in an Argand diagram. Then next, describe the geometrical shape formed by the points representing the roots and justify your answer. Okay, we'll first find the four roots first, then only we'll plot the 4 points on the Argand diagram, then only we describe shape. Okay, they want the roots in exponential form. So first of all, this is a polynomial equation. Hey, but look at this polynomial equation carefully. You don't really need to do factorization or guess the root and all that. You don't need those procedure because your Z only occurs in one term. Right? Like this is unlike z power 4 plus 2 z cubed plus 3 z squared minus z plus 1 equals 0. Like this is unlike such kind of polynomial equation where you have your z appearing so many times with different powers. So in this current question here, you don't need to attempt to factorize anything. You also don't need to try to guess the root and all that. Because z power 4, I mean z only appears in one term. Okay, so the first step that you should do is actually to rearrange this equation such that you have z power 4 equals to a complex number. And let's rearrange it to z power 4 equals to minus 1 plus z3i. Okay, so this is the first step that I will do. Okay, then I know that to solve for z is just to find the fourth roots of the complex number minus 1 plus z3i. Okay, so we follow the procedure as in example 9, where step 1, we will convert the complex number on the right hand side to become a polar form. And here we would prefer exponential form. We prefer exponential form because our final answer, they want it to be in exponential form. Okay. So modulus of minus 1 plus z3i, that is modulus of minus 1 squared plus surd of 3 squared, that gives me surd of 4, which is 2. Argument of minus 1 plus z3i, you visualize the Argand diagram. Minus 1 plus z3 is a point in quadrant 2. And you would need to go by pi and then reverse by the basic angle. So that's pi minus inverse tangent of modulus y over x. That's pi minus pi over 3. That gives 2 pi over 3. And now we can write the complex number minus 1 plus z3i in the exponential form, which is r is 2 e power I theta, where your theta is 2 pi over 3. Okay, so earlier we had the equation z power 4 is minus 1 plus z3i. Now this becomes z power 4 equals 2ei 2 pi over 3. Okay, next step, add the angle or add the argument by 2k pi. Okay, so don't forget this step. Again, if you happen to accidentally forget this step, later on, after doing the next few steps, you will realize that something is wrong because you won't get 4 solutions. If you forget the plus 2k pi step here, at the end, you are not going to get 4 solutions and you will realize that something is wrong. Okay. So next step, 2ei 2 pi over 3 plus 2k pi, where k is an integer. Okay. Next, it's time to move my power 4 over to the other side. I have 2 to the power of 1/4. Then I also have ei 2 pi over 3 plus 2k pi to the power of 1/4. Okay, so this 1/4, I'm going to multiply it into the 2 pi over 3 plus 2k pi. In 2 power 1/4, some people prefer to write it as a fourth root of 2. You can do that. However, this time I will just leave it as 2 to the power of 1/4. It doesn't really matter. So Okay, I don't need this square bracket anymore. It's just EI. Uh, I have pi over 6 here plus k pi over 2 close. 2 power 1/4. Okay, so here I will just do some algebra here. I'll make it to have a common denominator of 6 so that it's easier for me to observe what values of k to take later. At the top, I will need 1 plus 3k as the coefficient of pi. Okay, this is the time for us to decide uh, what values of k to take. Okay, so if you visualize your number line, by the way, you don't really have to draw your number line. And just visualizing it in your mind is good enough. 0, 1, and -1, obviously, these are the first three choices that you will take. Between -2 and 2, which one to choose? You have a dilemma. Here we have to choose 4 integers for k. Okay, so should we choose -2 or 2? You just check by substituting uh, -2 and 2 into this k here, colored in blue, and see which one will give you an answer in the principal range. Okay. So now, when I sub in k equals to 2, I will have 1 plus 6 as a coefficient of pi at the top. So when I sub in k equals to 2, I have 7 pi over 6, which is beyond pi, and I should not take it. That means -2 is a choice, 2 should not be taken. And if you really check, when you sub in -2, you will get -5 at the numerator. And -5 pi over 6 is within the principal range. Yep, so now that we have decided, we should take -2. We'll just write down -2, -1, 0, 1. Okay. So at the end, just write down your 4 solutions, substituting in your k. Okay, so you have EI, when you sub in -2, you have -5 pi over 6, followed by 2 power 1/4. EI, when you sub in -1, you have uh, -2 pi over 6, which is -pi over 3. When you sub in 0, you will get 2 to the 1/4 e power I times uh, 1 pi over 6. And when you sub in 1, ei 4 pi over 6, which is 2 pi over 3. Yeah, so here are your 4 solutions. And these are your values of z. Because we are solving the equation that involves z power 4. And so this is good enough as a final answer. Because they're asking us to solve the equation, solve for z, and now we got z as the final solution. Okay. Next step, next task is to show the roots in an Argand diagram. Okay, so when showing the roots in an Argand diagram, we will try to draw our diagram as accurate as we can, so that it will look nice, and later it will be easier for us to figure out what geometrical shape it will be. So we'll try to be as accurate as we can. Okay, when you draw the axis on paper, please use ruler to draw. The axes are supposed to be drawn using ruler when you're doing it on paper. Okay. Uh, right. So we do not need to convert all these roots into Cartesian form because that will be unnecessary. That will be an unnecessary trouble. Eh, When we have the exponential or modulus argument form, just by looking at the modulus n argument, we can already plot the points on the Argand diagram. Eh, We don't need to convert to Cartesian form. Okay, now, the modulus of 2 power 1/4, it tells us that all these 4 points, they are equidistant from the origin. All these 4 points, they are equidistant from the origin. And next, um, all the pink colored arguments here, this will be the angle measured from the positive x direction to the vector representation of that complex number. Okay, so let's plot the easy one first. The argument of pi over 6. Pi over 6 is 30 degrees. So when you measure your pi over 6, uh, because you are not expected to bring protractor uh, for your maths paper, they don't really expect you to measure 30 degrees very accurately, but at least you should know that 30 degrees is not very big. I mean, it's less than 45 degrees. 30 degrees is less than 45 degrees. You have a 90 degrees here. If 45 degrees is right in the middle, then 30 degrees should be below 45 degrees. Then only it would make sense. So although they don't expect you to be 100% accurate to measure 30 degrees, you don't really need to use protractor, but at least your line should be slanted in a not too steep direction. It should be below the 45-degree line. Now, because you already know that later your other 3 points will also be equidistant from the origin, and then I will suggest you to use a ruler to measure the length of this red line that you are drawing right now. Like the length of this red line is actually up to you to decide. Like let's say if you choose to use 2 cm here, and then later when you draw the other 3 roots, then you should also use 2 cm measured from the origin. Okay. Right, so this will be pi over 6. And so label your angle here as pi over 6. And here you plot your point. Yeah, I'll just indicate this. Like I will just write the root here. 2/1/4 e I pi over 6. So that people will know at this point it's actually at a distance of 2 power 1/4 away from the origin. Now, my next one, I will plot the 2 pi over 3. Okay. So 2 pi over 3 in degrees is 120. Pi over 6 is 30. This is 30 degrees. This is 120 degrees. So they differ by 90 degrees. 30 and 120 differ by 90 degrees. So you should expect to have a right angle. You expect to have a right angle over here. You expect to have a right angle here. So it's not a must to label the right angle here, but at least your diagram, it should appear to be an L shape. And one more thing, some people prefer to draw this red line using dotted line. You can do that as well. Uh, yeah, in fact, it will look nicer if you draw it using dotted line. Yeah. So I'll just change my red line to become dotted because during the exam you'll be drawing everything in pencil. So it won't look so messy if you draw this red line in dotted lines. Okay. Yeah, so just now I mentioned that if you have drawn your red line having a length of, let's say, 2 cm, then you should use the same length when you draw your second root. Okay, so this would be 2 to the 1/4 e I 2 pi over 3. And to indicate that this is actually the 2 pi over 3 direction, you can just label this angle here as pi over 3, then it should be clear enough. Okay. Right, the third point that I will draw will be negative 5 pi over 6. Okay, negative 5 pi over 6 in degrees is actually negative 150 degrees. You just need to punch in pi equals 180, then you can easily convert into degrees so that it's easier for you to gauge where the direction is. Okay. So minus 150 degrees, it will have a 180 degrees difference with positive 30. Okay, so that means it will be a direct continuation of the 30-degree line on the other side. Okay, so it's just the 30-degree line that you already had on quadrant 1 extended to the other side. It is a direct continuation. So put it here. This will be 2 to the 1/4 e I minus what was it? 5 pi over 6. Okay, and the last one, and by the way, to indicate that this angle is negative 5 pi over 6, I will just label a pi over 6 here, then it should be clear. Okay. Then the last one to label will be this angle, negative 60 degrees. And so this will have a 180-degree difference with positive 120. So it is again a direct continuation from here. And from your line in quadrant 2, and just direct continuation. And it's roughly here. And again, I will just label a pi over 3. Then people will know this direction in quadrant 4 will be the direction of minus pi over 3 radians. 2 to the 1/4 ei negative pi over 3. Okay. Okay, now notice that all my 4 dotted red lines are having equal lengths. They're having equal lengths. And I do have 90 degrees here. I do have another 90 degrees here. And pi over 3 plus pi over 6 are also 90 degrees. So we also have another 90 degrees here and here. So in other words, our red lines, actually intersect each other at 90 degrees. Okay, and since the distance from origin to each of the 4 points are the same, okay, so when we connect these 4 points, the question didn't really ask us to connect the 4 points, they only asked us to show the roots in an Eigen diagram. Okay, and by the way, I think it would be good to just label this as 2 power 1/4, okay, so that people will know this length represents 2 power 1/4 units away from the origin. Right, so our diagram is done actually. For the second task, show the roots in an Eigen diagram. This diagram is now complete. And the last task of describing the geometrical shape, it might be helpful to just connect the 4 points. It's not a must to connect the 4 points since the question didn't ask for it, but to make it easier for me to see, what the shape is, I guess it might be good to connect the 4 points. And it should be obvious that this is a square. This is a square where the two diagonals bisect each other at 90 degrees. And the distance from the origin to each of the four vertices are also the same. So this is actually a square. It satisfies the characteristics of a square because the diagonals bisect each other at 90 degrees and also the two diagonals have the same length. Yeah. So the description, I think I've already printed out for you in the notes. And so the points form a square. And they say justify your answer because the diagonals are perpendicular to each other and of equal length. So this is the description for the final part of the question. Okay, I think to make this justification more complete, let me just modify it a bit. Okay, since the diagonals bisect each other at 90 degrees, and have equal length. Yeah, then this reasoning will be more complete. Because the printed reason there didn't mention about bisect. Bisect means they cut each other into half. Yeah. Okay, so this is the answer for the description of the geometrical shape and also the justification. Okay. That's all for this video. In the next video, we'll start section 10.2 locus.